Hey everyone, my name is Maskaram, and in this video we are going to do a quick review of Bode plots. So I have 6 examples over here, and the idea is that in each example we will look at the transfer function, and then we will look at what the Bode plot looks like, or what does the gain plot and the phase plot looks like for each transfer function. So the first 3 examples are very simple transfer functions. The idea is to just to warm you up a little bit, and the transfer functions are simple enough that you can just look at it and just see or imagine what the Bode plot would look like without necessarily doing any kind of derivation. Example 4, 5, and 6 are a bit more complex, a bit more involved, but also more practical. So, for example, in example 4, we will look at the type 2 PLL open loop transfer function and the Bode plot for that. In example 5, we are going to look at transfer function of a CTLE, which is a common block in SERDES. That's the continuous time linear equalizer. And example 6 is noise transfer function. So noise transfer function, not the signal transfer function, of a delta sigma ADC. All right, so before we start, I want you to recall that usually we have this form in which we like to see our transfer functions. So as a prefix of this equation, we have the DC gain, and then any S terms at the top, those are the zeros, and any S terms at the bottom, those are the poles. All right. Okay, so let's start with the examples. Number 1 is going to be S over S plus 10. So just by looking at this example, right, you can see that there's one pole and one zero. The pole is at omega 10 and 0 is at omega of 0. So if I were to draw this on the S-plane, it would be a 0 at 0, and then a pole at omega of minus 10. All right, and on the so that's what the gain plot would look like. There's a 0 right at the beginning, and then we have a pole at omega of 10, right? And yeah, from right after 0 we see 20 dB per decade rise until we hit the pole, and then the gain flattens out. So pretty straightforward. And let's look at the phase plot. So one thing I want you to know is, since this we have a 0 at omega of 0, so then our phase will start from plus 90, and then there's this thing that since the pole is at omega of 10, the phase is going to drop, right? It's going to drop from 90 to 0, but we at omega of 10, the phase will be plus 45. And actually, the phase, whenever there's a pole, the phase will start dropping 1 decade before the pole frequency, and it will keep dropping until 1 decade after the pole frequency. So let me explain what I mean here. So here in this graph, 10 is the pole frequency, right? So 1 decade earlier, which is an omega of 1, the pole the phase will start dropping. So sorry. So when we hit this point, the phase will start dropping, and then at omega of 10, we would be at the midway, which is plus 45 degree, and then 1 decade after, which is 100, our phase will hit 0. All right, so that's what I mean by, the phase will start dropping 1 decade earlier, and it will keep dropping 1 decade after the pole frequency. All right, so that was a pretty simple example. Then example 2 is, again, just 2 poles here. So that's pole number 1 and pole number 2. And then I said that the pole frequency of FA is smaller than FB. So just looking at this transfer function, you can see that the DC gain is 1. Which is 0 dB, and then pole is at FA. There's another pole at FB, and again, the DC gain is 0 dB to start with, and then we hit a pole at FA, a pole at FB, and yeah, after the second pole, we'll be falling by 40 dB per decade, right? And then phase plot is also very simple. You start from 0, and then again, 1 decade before FA, which is FA over 10, the phase starts dropping. And then at FA, which is the pole frequency, you would be at minus 45, right? And then the phase will keep dropping until 1 decade after the pole frequency, which is 10 FA. And that's when you hit minus 90. And all of you have gone through from 0 to minus 90 because of the first pole, which is FA. And then similar thing for FB, the phase will drop another 90 degrees because of FB. So pretty straightforward, right? All right, let's look at example 3. So here the only different thing is we have a current input and a voltage output, and this is a low-pass filter. So you can derive the KCL, or you can derive the transfer function over here, whichever way you like. But at the end of the day, you will come up with this expression here. And so what that means is, for example, this R is the DC gain, right? And then looking at this transfer function, there's no 0, and then pole is at 1 over RC, right? So that's what I've mentioned over here. DC gain is at R, and then pole is omega of 1 over RC. So yeah, DC gain 20 log of R, by the way, and at 1 over RC we will see a pole, and then the phase will start dropping. Oh, sorry, the gain will start dropping by 20 dB per decade. Okay. Again, phase plot, very simple. You go from 0 to 90, and at 1 over RC, which is the pole frequency, you would be at minus 45, right? So, okay, so those were the straightforward examples. Example 1, 2, and 3, just one pole, 1, 0. Then example 2, we had 2 poles, and example 3, we had 1 pole, the only difference being that instead of voltage input, voltage output, we have a different quantity at the input and a different quantity at the output, but you can still write the transfer function V out over IN, and that would basically characterize this low-pass filter. All right, so example 4 is type 2 PLL open loop transfer function. So here, in a type 2 PLL, basically we would have over here I've shown this block and this block. So the first block is actually a combination of 3 different analog blocks in a typical PLL. So this would be like, so this would be the transfer function of phase frequency detector, and then there is a charge pump, and then there's a low-pass filter. And I have basically written the transfer function of all of these 3 combined into this one block. All right, and then the second block is just the VCO. So that's what you would have in a typical PLL. Notice that this is an open loop transfer function, not a closed loop. So we don't see a divider or a feedback network in this example. But you could also, just like we would derive here, the open loop transfer function, you could apply the same principles and derive the closed loop transfer function of a type 2 PLL. Okay. All right, so let's look at the type 1 PLL derivation. So if we have a system diagram like this, then we could just write the transfer function for this open loop. Let me call it HOL of S. Oops. So that would be the first block, which is ICP. That's the charge pump current divided by 2 pi, and then 1 over SC1. So C1 is the loop filter capacitor, and then R1 is the loop filter resistor. And then, so that's the first block multiplied by the VCO. So that's KVCO, which is the gain of the VCO, and then S. Okay, so then I can simplify it to the form that we usually look for. Let me pull out all the constants here. So the charge pump current 2 pi, and then maybe I could write SC1 as a common denominator, and then I could write SR1 C1 plus 1 multiplied by KVCO divided by S. And then I can try to pull out all the constants. So that would be the charge pump current 2 pi KVCO and C1. So that will be the DC gain multiplied by, so then we have an S term at the top, SR1C1 plus 1. So that will be the 0. And we have two S terms at the bottom, which are the poles at origin. So that is our transfer function for open loop transfer function for a type 2 PLL. So yeah, looking at that, let me just label it 0, and these are two poles at origin. So notice that there are two poles at origin, and just hold on to that thought and let us draw the Bode plot, and then we will look. We'll come back to that. All right. So the Bode plot will look something like this. We have two poles to begin with at origin, right? So we would have one pole. Oh, sorry. One pole over here, and then another pole over here. So two poles to begin with, and so we would right away start dropping at minus 40 dB per decade, and then we have a 0 later on, somewhere around here, and then we, our fall rate decreases by 20 dB. So now after the 0, we will fall by minus 20 dB per decade only. And so again, phase plot, because we have two zeros at the beginning, at at the origin, so we start off at minus 180 degree phase shift, and then because of the 0, our phase reduces by 90 degrees. All right, and this is what it would look like on the S plane. We have two poles at the origin, and then a 0 in the left-hand plane. All right. So one thing I want you to notice is, like I said before, there's two poles at the origin, right? And that's why we call it a type 2 PLL. Essentially, the name comes from the fact that there's two poles at the origin in the open loop transfer function. So if you look at type 1 PLL, equivalently, you could derive the transfer function for a type 1 PLL open loop transfer function, and what you would find is that there's one pole at the origin. So type 1 or type 2, that naming comes from the fact that there's a certain number of poles at the origin in the open loop transfer function of a PLL. All right. So yeah, that's the Bode plot for type 2 PLL open loop transfer function. And then let's look at the next example, which is transfer function of a continuous time linear equalizer. So this is a very common block in a typical SerDes. And over here, I've shown the circuit. Sorry. So that's a circuit. And basically, the way to derive the transfer function is first you can take differential half circuit, so just this part, let's say, and draw the small signal for it. So I have that over here, right? And then I've mentioned what I mean by Z1 and Z2. It's just that I've combined the passives, and then, or I've just mentioned the passives as Z1 and Z2. By passives, I mean these passives, right? And then once you have this diagram, you can solve based on KCL at this node and this node, and what you would get is a final expression V out over V in, which is something like this. Or simplifying it to our typical transfer function form, it would be something like this. So looking at this transfer function, you can see that this would be the DC gain, right? There's 1, 0 here, so that's the 0. And then there's a pole. So the pole frequency would be all of this. So that's pole. All right, so I mentioned the same thing over here. And then if you look at the transfer function, first we have this DC gain, right? And then we hit 0. So that's the 0 over here at 1 over RSCS. And then we start rising up by 20 dB per decade. And then we hit a pole. And then the gain flattens out. So that's the pole frequency. And eventually this this gain will also fall off because of like parasitic capacitances. You would see that after a certain frequency, this gain won't remain flat for like till infinite frequency. It will start dropping at some point. That's basically what I wanted to show with this dotted line here. And so this factor here, like from here to here, you can see that we basically boosted the high frequency components, right? So this is typically called CTLE boost, this quantity, and yeah, the idea is that you can increase or you can try to increase like CTLE boost as much as possible for any given channel, channel response, basically. Uh, and so, yeah, over here you have the gain plot. So again, you hit a 0, get some you get some phase from 0 to 90, and then you hit a pole, and then you go back from 90 to 0, right? So that's pretty straightforward. Yeah, so that is a pretty common block for SerDes. So let me, I guess, put this in context, right? So you would have, in a typical wireline transceiver, you would have a TX, and and then there would be a channel. So let's say this is a channel, and then you would have an RX, right? And so the idea is that you want to send an electrical signal, or let's say you want to send bits from TX to RX with as little distortion as possible, right? But what happens is this channel has a low pass response. So what that means is that um, the channel would basically reduce or basically it will attenuate any high frequency contents in your signal. And so how do you deal with that, right? One way would be to have another transfer function somehow that would uh, counteract the low pass response of the channel. So imagine if I have a transfer function like this, right? It's sort of like opposite of what the channel low pass filter looks like. So what would happen is when you multiply these two, you would get a response um, that is constant for a larger bandwidth, right? So that's great because we have sort of counteracted the effect, the low pass effect of the channel, and we have done that by boosting um, the frequencies, the high frequency components. So this is basically the CTLE, right? This um, this part, sorry, this part is the CTLE. And if you go back and look at this transfer function, that's basically it, right? It's just basically um, counteracting a low pass response from the channel. All right. So hopefully this example makes more sense now, and let's move on to the next example. So here we're looking at the noise transfer function of a delta sigma ADC. More specifically, we're looking at the delta sigma modulator, and this is the first order delta sigma modulator. So that's okay if you're not aware of it. Basically, the circuit is something like this. You have a summing node or a summing amplifier, then you have an integrator, and then you have a comparator. And the idea is that the comparator adds some quantization noise. So that's mentioned over here. So that's the quantization noise added, and I have denoted it by EI. All right, and then the signal is fed back through a DAC back to the input. So here, this is basically a 1-bit ADC, which is a comparator, and this is a 1-bit DAC, which is basically a switch, right? So let's look at the S-domain modeling for this ADC, this one 1-bit first order delta sigma ADC. So here we have the summation amplifier, that's the integrator, and then comparator is basically, since it is a 1-bit ADC or a comparator, it's just letting the signal through. And so in the S domain, it's modeled as a wire, but we have to model the EI, which is the quantization noise added in the loop. Similarly for the DAC, again, it's just letting the signal through, so it's modeled by just a wire over here. All right. Okay, so now that we have our S-domain model, one thing you would have to do is, since this is the noise, this example is about the noise transfer function of the delta sigma ADC, not the signal transfer function. So signal transfer function would be V out over Vn. Noise transfer function in this case is V out over EI, which is basically telling you how much quantization noise EI, when it's added into the loop, how much of it is going to the output, right? And so we can redraw this, as domain model by having EI as the input and V out as the output, and then you can derive the transfer function V out over EI, which is basically would be forward loop divided by 1 plus loop gain, and you would end up with this transfer function over here, or I should say this transfer function over here. All right, and that shows us that there's some DC gain over here. Oh, sorry. DC gain over here, and then there's a 0 and a pole. So if you plot it, this would look something like this. You have a 0 at omega of 0, and then you rise up at 20 dB per decade when you hit and then you hit a pole, and then the gain is flat from then onwards. All right, so that's pretty straightforward. Now, the idea behind this noise transfer function is a concept called noise shaping in oversampling ADCs. So take a good look at this transfer function, right? This is the noise transfer function tells you how the noise would be treated in an ADC, in this example, in an ADC, right? So any noise that comes in is going to see this transfer function, this high pass transfer function, right? So over here, I have this example of a delta sigma ADC with a noise transfer function, which is a high pass, right? The same thing that we have derived, that we have shown above, right? Over here. So imagine if you have a signal that is shown in the blue over here. That's your signal, and then there's some white noise, around the signal. So that's at the input of the ADC. And since the ADC has this high pass response, what would happen is this noise, the noise that was white, will actually get shaped. Sorry, trying to choose colors here. This noise will get shaped like this because it's a high pass response, right? So the noise is sort of like pushed out of band, and so again, you have your signal just like before over here. But look, the SNR in this case, the SNR over here, and look at the SNR or signal to noise ratio over here. Your SNR is better, right? And so that's the idea of like delta sigma noise shaping. Basically, you're trying to push the noise out of band, and that helps you get a higher SNR in a delta sigma ADC, and so that's the the Bode plot for a noise transfer function for a delta sigma ADC. All right, so that is pretty much it for this video, and I'll see you in the next one. Cheers.